Hello, everyone. I want to take you throughout a series of slides here. Hopefully, it will help you to prepare for any general chemistry exam you want to take. So, if you look at the first slide here, it is talking about the Chatelier principle. Okay. So the Chatelier principle states that if a system at equilibrium is subject to a change of pressure, temperature, or the number of mole of a component, there will be a tendency for a net reaction in the direction that reduces the effect of this change. So look at the chart below. I give you an example of a system equation and the change and the result that change cause. So the first reaction here, when you look at the first reaction, when you add a drying agent to this reaction, a dry agent, what a dry agent will do, a dry agent will actually dry water. Okay, it will dry the H2O. So when the H2O is drying, its concentration will decrease. So when the concentration of H2O decreases, the reaction will shift to the right. So this is the reaction. The reaction will shift to the right. Okay. The reaction will shift toward the formation of the product. That's what this means. Okay, so if you continue to remove the water, okay, with a dry agent, if you continue to remove, the concentration of water is decreasing, the reaction will keep proceeding toward the formation of the product. So let's look at the second reaction. So if you look at this reaction, there is no nitrogen that is involved in the equation on the side of the reactant and on the side of the products. So if you add nitrogen to this reaction, what will happen as a result? No change, because nitrogen is not a component of this reaction system. Okay, let's move to the third reaction. For the third reaction, what will happen if the reaction is carried out in an open container? So look at the result here. Because hydrochloric acid is a gas that can escape from the system, the reaction is forced to the right. This is the basis of the commercial production of hydrochloric acid, open container. The hydrochloric acid is a gas, that means the volume will decrease. Okay, we are producing hydrochloric acid in an open container. It means that the concentration will decrease, or the gas will decrease. So the reaction will keep proceeding to the right. Okay, we go to the right toward the formation of the product. Okay, so look, if you look at all the reaction here and the change that occur, you can actually read about the result that the change will produce for the rest of the reaction on this slide. Okay, let's move to the next slide. How to change in temperature affects equilibria of endothermic reaction. So endothermic reaction is the reaction that actually absorb heat, consume heat. So the reaction needs the heat in order to proceed to the formation of the product. So if you look at this reaction here, if we raise the temperature, what raise the temperature mean here? If you raise the temperature, that means you are providing, you are bringing a heat in. If you are bringing heat in, what will happen to this reaction? The reaction will shift to the right. More product will fall, increase. More product will fall. The reactant will decrease. The quantity of the reactant will decrease. How do change in temperature affect equilibrium for exothermic reaction? Okay, we just talked about what happened in the case of the endothermic reaction. So for the exothermic reaction is the opposite. Okay, so exothermic reaction are reaction that produce heat. So when you are bringing more heat in, the reaction will reverse. Okay, the reaction will reverse back to the formation of the reactant. Okay, now this slide show a sample of KSP problem that have been already solved. You have the answer of the problem here. So the problem itself is about the calculation of the solubility of Ag plus and the Cl minus silver ion and chlorine ion. So they actually give you the KSP, okay, of AgCl. So the value of KSP of AgCl is 1.8 times 10 to the power minus 10. What will be the molar concentration of Ag plus and Cl minus in pure water placed in contact with solids AgCl? Okay, so you are actually given the KSP, okay, of the compounds, and you are asked to calculate the molar concentration of the ion the compound will dissolve into. Okay, when the compound is dissolved into a solution. So this is the KSP formula. So it will be AgCl dissolving into Ag plus Cl minus. So the KSP can be calculated by multiplying the concentration of Ag plus times the concentration of the chlorine ion. So we know the KSP, okay, 1.8 times 10 to the power of minus 10. So if the two concentration of the Ag plus and Cl minus are X, okay, so X, those are the two concentration. You know, you have to use stoichiometry here, okay, from to actually calculate those concentration. So 1.8 times 10 to the power minus 10 equal to x times x. So is a square, x square up. So x should be the square root of 1.8 times 10 to the power minus 10, which is 0.000134416 molar. So the scientific notation is 1.3416 times 10 to the power minus 6. Okay, let's move to the next slide. For this one, you are given the molar solubility. You are given the molar solubility of lead chloride. Okay, so you have to calculate the KSP. Let me help you here. So the molar solubility of lead chloride PbCl2 in 0.10 molar of NaCl is 1.7 times 10 to the power minus 3 mole in a liter. Okay, so molar. Now that is 1.7 times 10 to the power minus 3 mole of PbCl2 will dissolve in 1 liter of the solution. What is the KSP? What is the KSP of Pb lead chloride? What is the KSP? So lead chloride will dissolve into solution into lead ion and chlorine ion. So if you actually balance the equation, okay, if you balance the equation, it will give you Pb plus 2 Cl minus. Okay, so if you came over here, so KSP is equal to the concentration of Pb plus times the concentration of Cl minus by the square up. Because stoichiometry is when you take this one, the concentration of lead ion, the concentration of Cl minus the chlorine ion should be 2 times the concentration of lead. So they multiply this by 2 to get to 3.4 times 10 to the power minus 3, and you square it up. Okay, so they gave you KSP equal to 1.965 times 10 to the power minus 8. Okay, stoichiometry talking, when you start with n mole, for example, n mole of Pb, this should be lead chloride, no lead iodine. Okay, so it has to be corrected here. So lead chloride will give you n mole, will give you n mole of the ion, lead ion, plus 2n mole of Cl minus. That's how we get to this. That's how we obtain the 3.4 times 10 to the power minus 3 is 2 times this concentration here. 2 times this concentration, we get this concentration and square up. Okay, so if you do the calculation, you will find KSP equal to 1.965 times 10 to the power minus 8. Quickly, let's move to the next slide here. So what are the molar concentration of ion in solution when solid lead iodide, okay, is in contact with pure water? Now lead iodide will dissociate into water into lead ion plus iodine ion. So you have KSP is equal to the concentration of the lead ion times the concentration of iodine square up. Okay, so if you move, you start with x mole of lead iodide, you're gonna have in solution x mole of lead ion and 2x mole of iodine ion. Okay, so that's what they use. We use that to calculate the KSP. Now we plug. We want to calculate, actually calculate the concentration. Okay, molar concentration of lead ion and iodine ion. So this is what you get when you plug the KSP here. It's x times 2x squared. Cubic of x is this. So x should be equal to this one for lead ion, and then equal to this one, equal to this value here for iodine ion. Okay. Next slide is about the calculation of the pH of a buffer. We have a sample problem here. I'm gonna read, calculate the pH of a buffer solution. pH of a buffer solution at 298 Kelvin, prepared by mixing 25 cubic centimeter of 0.1 molar acetic acid and 25 cubic centimeter of 0.10 molar sodium acetate. Okay, so you're gonna apply, this is the formula, okay, you need here to calculate the pH of this buffer. And when you apply the formula with the pKa, the Ka is given to you. Okay, the Ka is already gave it to you. The acid ionization constant Ka. Okay, you have a 1.8 times 10 to the power minus 5. Okay, so pKa should be what? pKa should be 10 to the power of minus Ka. So that's pK should be a minus log at base 10. Okay, minus log pKa is minus log of the Ka. That's what it is. Okay, no, not 10 to the power of no. It's minus log. So that's what we apply here, plus log of the base over the concentration of the weak acid. It help you. This is what we got for pH equal to 4.74. Because the two concentration are the same, we have pH equal to pH is equal to pKa. Okay, as you can see here. But if the two concentrations are not the same, pH will be different from the pKa. Okay, value. So you can look at this problem, solve it, okay, yourself, and get to understand the concepts. Okay, so you have to remember the formula Anderson, the equation here, Anderson equation, in order to do the calculation. Okay, so also look at the calculation of the pH of an acid. Okay, on this slide here we have, let me read, is what is the problem. The problem is what is the pH of 0.05 molar NaClO sodium hypochlorite, okay, solution if the concentration, or if the Ka for hypochlorous acid HClO is 3.0 times 10 to the power minus 8. Okay, so you have to proceed. This is a partial dissociation of the acid. Is the equation here. Stoichiometry talking, if you start initial, if we have 0.05, but in solution the NaClO will give you this ion, Cl minus ion, that will combine with the H2 to actually form the hypochlorous acid. Okay, and hydronium ion. So we're starting with 0.05 mole of the ion here, and at another instant Okay, the reaction is proceeding slowly here. So there is a partial dissociation. So if X mole dissociate, okay, into solution, if X mole dissociate, you have to subtract the X from the mole, the initial mole you have here. So it will give you X mole of hypochlorous acid and X mole of hydronium ion. Okay, and this is very, very important. This stoichiometry, what we are using here is very, very important, and because you're gonna use in order to determine the pH, you're gonna use the base ionization constant Kb of the hypochlorous acid. Okay, so it should be given to you somewhere. You have Kb. Now in the equation, this is the equation of Kb. So you have Kb equal to X times X. Okay, which are the concentration of the hypochloric acid, here, and the hydronium ion. Okay, on the top of the bar here, multiply X times X divided by the 0.05 minus X. Now X is very small. The association is very small. The mole dissociate is very, very small. So 0.05 minus X is equal to 0.05 because X is negligible. Okay, X is negligible. So if you plug everything in here, we know Kb. You can calculate Kb. Okay, Kb is 3.3 times 10 to the power minus 7. If you plug it in the equation, you get the concentration of OH minus X. You can calculate X, actually calculate S, and X is equal to the concentration of OH minus. So we know that POH is what? POH is minus log to the minus log of OH minus concentration. So then you can calculate POH when you know the concentration of OH minus, and then you know you're gonna apply pH plus POH is equal to 14 to actually calculate the pH. Okay, pH is 10.11. pH is 10.11 here. So let's move to another problem here. This show the concentration of pH, the calculation of the concentration of pH for strong acid. Okay, so you have to apply this, the formula you apply to calculate the pH of a strong acid. So the problem is calculate the pH of a solution with this concentration of hydrochloric acid. So when hydrochloric acid dissociates into solution, it dissociates 100%. So stoichiometry talking, then you start with a number of mole of HCl, you're going to have the same number of mole of H plus in solution. So the number of mole here should be the same as the number of mole of H3O plus in solution. So that's what you plug into this formula in order to calculate pH. Okay, pH is 3.908.51. But it is good for you to don't just look at this, the solution, and read throughout it. You need like notebook, note sheets, and then solve this also, solve it yourself, and learn how to use the scientific calculator actually to solve those kind of problems. You need that. Okay, so when you understand the concept, when you go to your text or your exam to actually solve those kind of problems, it might not be the same because data can be different. So you can be able actually to use your calculator to find the answer. Let's move to the last problem here on this revision for exam. So look at this problem here. Calculate the pH of a solution containing 1.2345 times 10 to the minus 4 molar calcium hydroxide. Now the formula for pOH is here, is given to you here, but there is something particular with calcium hydroxide. Calcium hydroxide will dissociate, we start in solution, gives Ca2 plus, and 2OH minus. So when you start with X mole of COH2, it will give you the same number of mole of Ca2 plus, okay, and 2 times that number of mole of hydronium ion. So when you are applying the formula, POH is minus log of OH minus, the concentration of OH minus will be equal to 2 times the concentration here, okay, 2 times this 1.23, it gave you 2.46. So that's how you're gonna plug the concentration of OH minus inside the formula. So POH is equal to minus log of 2.46 then times 10 to the power minus 4. So you have POH is 3.6074. So when you know the POH, you can use the following formula, pH 14 minus POH, to actually deduct the pH of the compounds. So this ends our revision, short revision for any exam, a chemistry general exam you want to take. Okay, this revision will help you actually to feel comfortable when it comes to any problem you have to solve on your exam. I hope this adds something to your revision, the revision you are actually doing to prepare yourself for your upcoming exam. Okay, have a good day. Bye bye.